There is something out there pulling us. Not metaphorically, not poetically, literally, physically, with a gravitational force so immense and so relentless that our entire galaxy, the Milky Way, with its 400 billion stars, its spiral arms stretching 100,000 light years across, its ancient core burning with the fires of a supermassive black hole, is being dragged toward it. Every star you have ever seen in the night sky is moving. Every planet, every moon, every drifting cloud of cosmic gas is accelerating in the same direction. And the terrifying, humbling, almost incomprehensible truth is this: we do not know what is pulling us. We cannot see it. We cannot directly observe it. It hides behind the very heart of our own galaxy, concealed by thick walls of dust and gas and the blinding light of 100 billion suns. We have given it a name, because naming things is what humans do when they face the unknown. We call it the Great Attractor. And the more we learn about it, the more it unsettles us. The universe, at its largest scale, is not a smooth, uniform sea of matter and light. It is not a gentle, evenly distributed cosmos where galaxies float like leaves on still water. The universe is violent, structured, and shockingly asymmetrical. Galaxies cluster together into groups, merge into clusters. Clusters cascade into superclusters, colossal architectures of matter that stretch for hundreds of millions of light years in every direction. And threading through all of it, like the tendons of some unimaginable cosmic skeleton, are vast filaments of dark matter and gas, the cosmic web that gives the universe its shape. Within this web, matter does not sit still. It flows, it streams, it falls, always, endlessly, inevitably, toward the densest concentrations of mass. This is what gravity does. It pulls everything toward everything else. And where mass is greatest, the pull is strongest. The Great Attractor is one of those places. It is a region of space so dense, so gravitationally dominant, that it draws not just our galaxy, but an entire supercluster of galaxies. The Laniakea supercluster, 500 million light years across, containing more than 100,000 galaxies, steadily, irreversibly toward it. To understand the Great Attractor, you first need to understand the scale of the universe in which it operates. Most people understand intellectually that the universe is big. They have heard the numbers. They know that light travels at 186,000 miles per second, and that even at that speed, it takes 8 minutes to reach us from the sun, 4 years to reach us from the nearest star, and 2.5 million years to reach us from the Andromeda Galaxy. They know these numbers. But knowing a number and truly grasping it are entirely different things. The distance to the Great Attractor is approximately 250 million light years. This means that the light arriving at our telescopes from that region of space left its source when the dominant life forms on Earth were early reptiles, when the dinosaurs had not yet appeared, when the continents were arranged in configurations that would be unrecognizable to any geographer alive today. The universe was already billions of years old, and the light has been traveling toward us ever since, crossing an ocean of space so vast that the human mind simply does not have the architecture to contain it. Yet, across that ocean, across that almost inconceivable gulf, the gravity of the Great Attractor reaches us. It reaches us, and it moves us. The story of the Great Attractor's discovery begins not with a telescope pointed at the sky, but with a puzzle embedded in the data. In the 1970s and early 1980s, astronomers studying the motion of galaxies noticed something deeply strange. The expansion of the universe, set in motion by the Big Bang nearly 14 billion years ago, should cause galaxies to move apart from each other in a relatively predictable pattern. The farther away a galaxy is, the faster it should appear to be receding from us. A relationship described by Hubble's law, one of the foundational observations of modern cosmology. But when astronomers looked carefully at the actual motions of galaxies in our cosmic neighborhood, they found deviations, systematic, large-scale deviations. Galaxies were not moving exactly as Hubble's law predicted. There was an additional motion, a peculiar velocity, that ran counter to the general expansion. A river of galaxies was flowing, and it was flowing in a specific direction, toward a region of space in the direction of the constellations, Centaurus and Hydra. Something was pulling them. Something enormous was there, And it was, pulling everything in this corner of the universe toward it with a gravitational force that made the general expansion of the cosmos look, in comparison, like a gentle current fighting against a powerful tide. The problem was that the region where the Great Attractor appeared to be located was almost perfectly hidden from our view. The core of the Milky Way sits between us and that patch of sky, and the core is an impenetrable maze of dust clouds, molecular gas, and stellar crowding so dense that visible light cannot pass through it. Astronomers call this the Zone of Avoidance, the band of sky along the galactic plane where our own galaxy blocks our view of what lies beyond. It is one of the great ironies of our cosmic position. The very galaxy we live in conspires to hide from us one of the most significant gravitational structures in the universe. Early attempts to identify the source of the peculiar velocities were frustrated by this obstruction. Astronomers could measure the effect, the unmistakable tug of something immense, but they could not see the cause. The breakthrough came in stages as technology improved and new observational strategies were developed. Radio telescopes and X-ray observatories operating at wavelengths of light that dust cannot block began to penetrate the zone of avoidance and reveal what lay behind it. What they found was staggering. The region around the Great Attractor was not empty space. It was packed with galaxies, a dense, sprawling concentration of galactic mass on a scale that had rarely been seen elsewhere in the observable universe. And at the center of this concentration, like a beating heart of gravitational dominance, was a supercluster of galaxies known as the Norma Cluster, officially cataloged as a Bell 3627. This cluster alone contains hundreds of galaxies, many of them giant elliptical systems, each containing hundreds of billions of stars. The combined mass of the Norma Cluster and its surrounding environment is somewhere in the range of 10,000 trillion times the mass of our Sun, a number so large that it is essentially meaningless as a quantity and can only be understood in terms of its effects. Its effect is the Great Attractor. Its effect is the slow, relentless gravitational current that is drawing the Milky Way and everything around it in its direction at roughly 600 kilometers per second. 600 kilometers per second. That is the speed at which our galaxy is falling toward the Great Attractor. To put it in terms that might carry some visceral weight in the time it takes you to read this sentence, the Milky Way will have moved roughly 3,000 kilometers closer to the Great Attractor. In a single day, it moves more than 50 million kilometers in that direction. In a year, it covers nearly 20 billion kilometers of the journey. And yet the destination is so far away, 250 million light years, that even at this speed, it would take billions of years to arrive. This is the nature of cosmic motion. It is simultaneously breathtaking in its speed and humbling in the distances involved. The universe is so large that even the fastest motions look, from the right perspective, like glacial drifting. But the Great Attractor itself, as astonishing as it is, turns out not to be the final word in the gravitational hierarchy of our cosmic neighborhood. As astronomers mapped larger and larger volumes of space, they began to realize that the Great Attractor was itself falling toward something, the enormous mass of the Norma Cluster and its environment, which seemed so overwhelmingly dominant at one scale, was merely a tributary in a larger river of cosmic motion. That river flows toward an even more massive concentration of matter, located roughly 700 million light years from Earth in the direction of the constellation Perseus. This structure, discovered in the 1980s and 1990s and studied intensively since, is called the Shapley Supercluster. The Shapley Supercluster is the most massive concentration of galaxies in the observable universe within 1 billion light years of Earth. It contains thousands of galaxies arranged in a complex web of clusters and filaments, and its total mass is so immense that it exerts a gravitational influence across an enormous fraction of the observable cosmos. The Great Attractor, which once seemed like the apex of gravitational dominance in our corner of the universe, is pulling us toward it. But the Shapley Supercluster is pulling on the Great Attractor as well. We are not merely falling toward one gravitational giant. We are falling in a chain, link by link, toward ever larger concentrations of cosmic mass. This realization prompted a fundamental rethinking of how cosmologists describe our place in the universe. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a landmark paper that redefined the boundaries of our home supercluster, using a new technique that mapped the flow of galaxies in 3 dimensions, tracking not just where galaxies are, but where they are moving. Tully and his colleagues identified the full extent of the gravitational basin to which our galaxy belongs. They found that the Milky Way sits within a supercluster far larger than previously recognized, a vast structure that they named Laniakea, A, Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 500 million light years and contains more than 100,000 large galaxies, including our own. Within it, all galactic motion converges toward the Great Attractor at the supercluster's core. The Great Attractor, in this picture, is not merely a distant gravitational curiosity. It is the central attractor of our home in the universe. We belong to a structure organized around it. We are part of its gravitational family. The implications of this for our understanding of the universe's large-scale structure are profound. The cosmic web, the filaments and voids and nodes that organize matter on the largest scales, is not static. It is dynamic. Matter flows along filaments toward nodes. Nodes grow, denser as they accrete mass from their surroundings. Superclusters like Laniakea are themselves temporary structures, not gravitationally bound in the way that galaxies and galaxy clusters are, but shaped by the competing pulls of gravity and the expansion of space. On the largest scales, the accelerating expansion of the universe, driven by the mysterious dark energy that makes up roughly 68% of the cosmos, will eventually overcome these gravitational flows and stretch the cosmic web apart. The Great Attractor will eventually lose its ability to draw matter toward it, as the expansion of space carries galaxies beyond each other's gravitational reach. But that dissolution lies in the deep future, billions of years from now. For the present, the flow continues. The river of galaxies runs on. What lies at the very heart of the Great Attractor? This question has driven some of the most ambitious observational campaigns in modern astronomy. Mapping the Norma Cluster in detail required instruments capable of seeing through the obscuring dust of our galaxy. Not just radio, telescopes, but also infrared observatories, which can penetrate the galactic plane more effectively than visible light instruments and X-ray satellites, which detect the hot gas that fills the space between galaxies and rich clusters. These observations revealed a complex and dynamic environment. The Norma Cluster is not a single, unified structure, but a system of multiple subclusters in various stages of merging. Galaxy clusters grow by consuming smaller clusters, and the Norma Cluster appears to be actively engaged in this process, with several infalling groups of galaxies in the process of being absorbed into the main structure. The collisions between clusters are among the most energetic events in the universe since the Big Bang. They release energies that dwarf even the most violent individual galactic events, heating the intracluster gas too. Temperatures of hundreds of millions of degrees and sending shock waves rippling across millions of light years. Within the cluster, individual galaxies tell stories of their own. Many of the large, elliptical galaxies at the cluster's core bear the marks of ancient mergers, the smooth, rounded shapes and complex internal structures that result from the gravitational interaction and eventual fusion of spiral galaxies like our own Milky Way. These elliptical giants are the old survivors of the cluster. Environment, their star formation long since quenched by the consumption of their gas reserves and the harsh conditions of life in a dense galactic neighborhood. Around them, smaller galaxies orbit, tidally distorted, some in the process of having their outer layers stripped away by the gravitational influence of their massive neighbors. The cluster is a system in motion, a system still evolving, and at its gravitational center, the most massive galaxies accumulate, growing ever larger through a process of slow, continuous cannibalism. The dark matter that underlies all of this visible activity is, in some ways, the most important ingredient of all. Dark matter. Matter that neither emits nor absorbs light, that interacts with. Ordinary matter only through gravity constitutes roughly 27% of the total mass energy, content of the universe. In galaxy clusters, it typically makes up about 80 to 90% of the total mass. The gravitational well of the Norma Cluster and the broader Great Attractor region is not primarily a well of ordinary, visible matter. It is a well of dark matter, an invisible scaffolding of mass that dwarfs the stars and gas we can see, and that is ultimately responsible for the gravitational flows that organize the cosmos on the largest scales. Dark matter cannot be directly observed, but its gravitational influence is unmistakable. The peculiar velocities of galaxies, the temperature of intracluster gas, the bending of light by gravitational lensing. All of these phenomena point to the presence of vast quantities of matter that we cannot see but cannot ignore. The existence of the Great Attractor and the structures associated with it also carries implications for some of the deepest questions in cosmology. The distribution of matter in the universe is not random. It reflects the pattern of tiny density fluctuations imprinted on the cosmos. In the first fraction of a second after the Big Bang, quantum fluctuations in the early universe that were stretched to cosmic scales by a brief period of exponential expansion called inflation. These fluctuations became the seeds around which matter accumulated over billions of years, growing under the influence of gravity into the structures we see today. The Great Attractor is, in this sense, the product of processes that were set in motion at the very beginning of time. Its existence, its mass, its gravitational influence, all of it traces back to a pattern established in the first moments of cosmic history. To study the Great Attractor is to read, in some sense, a chapter of the universe's origin story. There is something deeply unsettling about the Great Attractor, and something equally inspiring. The unsettling part is the sheer scale of the forces involved, forces against which human civilization, human history, human existence are utterly inconsequential. The Milky Way, with all its hundreds of billions of stars and all the life that may exist within it, is a grain of dust, caught in a current whose source is 250 million light-years away. We did not choose this. We cannot resist it. We are simply moving, as everything around us moves, toward a gravitational destination that was set before the Earth existed, before the sun was born, before the molecular cloud that would one day become our solar system had even begun to collapse. The Great Attractor does not know we are here. It does not care. It simply pulls, as gravity always pulls, indifferently and without end. But there is inspiration here too, and wonder of a kind that is available only to creatures capable of understanding the universe they inhabit. For billions of years, our galaxy drifted through space, its motion shaped by forces it had no way of knowing. Then, in a brief, extraordinary moment of cosmic history, the last 400,000 years or so, an eye blink in the life of the universe. A species evolved on a small planet orbiting an ordinary star, and that species developed the capacity to look out at the cosmos and understand what it saw. We built telescopes. We invented mathematics. We developed theories of gravity and light and space and time that allowed us to make sense of the universe's structure. And we discovered the Great Attractor, not by seeing it directly, not by traveling there, but by being smart enough and careful enough to read the subtle signals in the motions of galaxies and to infer the presence of something enormous behind the veil of our own galaxy's dust. That is not nothing. That is, in fact, one of the most remarkable things that has ever happened in the 14 billion year history of the universe. We are moving toward the Great Attractor. We have been moving toward it for as long as the Milky Way has existed, long before there was anyone here to notice. We will continue moving toward it for billions of years to come, though the accelerating expansion of the universe will prevent us from ever truly arriving. And in the meantime, we will keep looking. We will keep mapping. We will keep building better instruments and developing better theories and asking harder questions. The Great Attractor is hidden from us in many ways, by distance, by dust, by the limits of our technology and our understanding. But it is not hidden completely. Its gravity reaches us. Its influence shapes our motion. It has left its fingerprints on the structure of the universe, and we are learning, slowly and with great effort, to read them. In the vastness of a cosmos that is mostly dark and mostly cold and mostly empty, the fact that something pulls us is, in its own strange way, a comfort. The universe is not indifferent to structure. Matter seeks matter. And somewhere out there, 250 million light-years away, behind the blinding heart of our own galaxy, the Great Attractor waits, immense, invisible, and endlessly patient, as it has always, waited, and as it always will.